So I want to talk a little bit about leaving group abilities. All leaving groups should have two very important properties. The absence of either one of these properties really is a great hindrance to any kind of a substitution reaction. Number one, it must be more electronegative than the carbon atom to which it's attached. This brings us to an excellent discussion of the descending order of electronegativity, the infamous Fonkelbrish. So here are the first 9 elements on the periodic table. All of these elements meet the first criteria for being a good leaving group. They are more electronegative than carbon. And I want to point out that all of the halogens meet this first criteria. Criteria number 2. The leaving group must be capable of an independent existence. It must be stable. So let's talk about some groups that meet criteria 1 but do not meet criteria 2. Fluoride does not meet criteria 2. OH minus does not meet criteria 2. Any R group, any carbanion, neither meets criteria 1 nor criteria 2. NH2 minus does not meet criteria 2. These are not very good leaving groups. Groups that do meet criteria 1 and criteria 2 appear to be chlorine, bromine, and iodine. And in fact, iodine is the best in terms of obeying rule number 2, whereas chlorine is the best in obeying rule number 1. However, rule number 2 tends to be much more important than rule number 1 because iodine is still more electronegative than carbon, which activates it as an electrophile. It's its stability as iodide that makes it an exceptional leaving group. So one of the big problems in chemistry is when you don't have a good leaving group, how do you convert it to a good leaving group? And this is going to be in the case of reactions with alcohols. So let's say for a moment that we have 2-butanol, and let's make this a bit of a more relevant stereochemistry problem. This is a good time to pause this video right now and to ask yourself, is this R2-butanol or is this S2-butanol? And in order to do that, you have to assign some priorities. The OH is priority 1, the hydrogen is priority 4, the methyl is priority 3, the ethyl is priority 2. Since the low priority is oriented away from you, the viewer, you're going from 1 to 2 to 3, that is R. So this molecule is R2-butanol. Let's say we're going to react 2-butanol and we want to convert it to an alkyl halide. And we don't want to go through the normal SOCl2 reagent. We have some possibilities in making OH a better leaving group, and let's look at them. Number one is we can protonate it. I could use HCl as my source of Cl. I protonate, and now it's not OH minus that's your leaving group, it's water that's your leaving group. So we get a neutral, stable leaving group. This certainly works. Also, I can functionalize. My OH. It will still have a negative charge when it leaves, but it will be resonance stabilized. And there are three main functional conversions that I can make to enhance the leaving group of OH minus. One is called a tosylate. One is called a mesylate. One is called a triflate. So the tosylate has this structure. Of course, if we were to react it with our chiral alcohol, you would just have a simple SN2 reaction. I'm going to skip some detail here because you would get a tetrahedral intermediate, but the SO double bond would reform and chloride would be your leaving group, and then it would pull off of this proton via proton transfer reaction. So now once you've made this conversion, your leaving group is much more stable because of the significant resonance stabilization that you have. So this readily leaves. The mesylates and the triflates are going to be different structural analogs, and they're going to operate on the same premise. So this is the tosylate derivative of the alcohol that I've made, where this would be if I reacted with water. Of course, this would be an R group. But here's the tosylate group that's resonance stabilized. Here's the mesylate group. It simply has the sulfonyl group and a methyl group. Still significant resonance stabilization here. And the triflate simply gives you an added inductive effect by replacing the 3 hydrogens with 3 fluorines. I would say the tosylate is probably the most commonly used activating group for alcohol becoming a better leaving group. You can also see some of the arrow pushing that is involved in the chemistry that's mediated by these reactions. But the important part of this is that you've got significant resonance stabilization when the alcohol leaves. It will still be negatively charged, but it'll be resonance stabilized. So this now begs the question, what's the best possible leaving group that you can have in a substitution reaction? The answer is going to be I minus. I minus, then Br minus, then Cl minus, then water, then the mesylates, tosylates, and triflates. They're still very, very good, but the halides are the best, which is why in most organic textbooks you will see leaving group information and substitution chemistry lumped into when they introduce the alkyl halide. The alkyl halide is the prototypical substrate for an SN1 or an SN2 substitution reaction.